Okay, now it's working. So, what was it? Okay, so the underlying mechanism, the biological mechanism that creates competition between species can be classified usually in two types. The first is what is called the exploitative competition. So both species compete for a limited resource. So you have some resource, and you can there's no active. The competition does not require that one species actually has some mechanism of interaction with the other one. It's mediated by the resource. And therefore, this competition will depend also on the level of the resources available. Right? Because, well, if you have a lot of resources, then probably the competition will be weaker than if you have a lot of resources. If you have a few resources, then you expect to have stronger competition. Exploitative competition can also be further divided into in several types. So you can have a competition such that that the resource can be equally divided between all the individuals, in which case every individual gets a lower amount of resources. It is usually, this is connected to a smaller birth rate, has less energy. But you can also have competition where you have the kind of the winner takes it all. Okay, so you get the resource, you get everything you need, or you don't get anything. Right? So there's a different kind of situations. So the second kind of competition is what's called interference competition. And this is when the species actively interfere with one another. Okay? So both types of competition may exist. So interference competition, so it's not necessarily directed to the level of the resources. It's a direct interaction in this case. This is common, for instance, with birds, which have territories. Okay? So they interfere with other species, such that the other species cannot have access to resources. Okay? So they interfere. The same also happens with ants. Ants interfere with other species. They interfere means that they avoid the other species. That they act in such a way that the other species has no access to resources. So, but they don't necessarily. It's not to be. Don't make confusion with predation. They do not consume the other species. Okay? So competition is not consumption of other species. When you have more than one species, right, you call the competition as inter-specific competition. If you have only one species, you say that it's intra-specific competition. Here we will now study inter-specific competition. From the modeling point of view, we can have two different strategies. One strategy is to make a model that we will call implicit, which is, so now we are talking about exploitative competition. We can take a model such that I say I have competitor 1, competitor 2, but actually they only have, and then there's the resource. So I can take into account the resource or not in the problem. If I don't take the resource dynamics in the problem, then I say I have an implicit model. And if I take the resource explicitly into account, I say I have an explicit model. Okay? So we will follow here the traditional path for the modeling of competition. But I will comment at the end of the lecture different strategies from the modeling point of view that other than the one that I will now show you. Okay? So let's take two species. There's a type of completion. It's competition, implicit competition model, not completion model. And we will take into account the inter-specific competition and the intra-specific competition. Okay? And we will use now the same strategy, the same rationale as we did with the predation case. We want to write down equations and as simple as possible, like the Lotka-Volterra model, but for competition. Yeah, and actually what we will do is sometimes called the Lotka-Volterra model for competition or competitive Lotka-Volterra model. So we have to have two functions, N1 and N2, population 1 and population 2, two different species, species 1 and species 2, N1 and N2 are the population levels of these species. And in the absence of competition, we'll say that they have just a logistic growth. Each of them has a certain intrinsic growth rate, which is R1 and R2, and each species has associated carrying capacity K1 and K2. Okay? So two different species which grow logistically in the absence of the other. Okay? Now we want to write down the influence of species the influence of species 1 on species 2 and the influence of species 2 on species 1. We did this yesterday, and yesterday had a plus-minus interaction. So there was a positive term for the predator and a negative term for the prey. Here we want to have two negative terms. So N1 will influence N2 in a negative way and vice versa. So the easiest thing to do is just proceed as yesterday and say, now I have the logistic and the growth rate N1 of N1 is influenced negatively by N2, and N2 is influenced negatively by N1. A and B is the kind of phenomenological parameter that says how strong the influence is. Okay? So that's the model, actually. Now, you have been presented to the Lotka-Volterra competition model, and now we will go for a little bit of mathematics. Okay? I mean, not very complicated mathematics, but today we will have more calculation than usual. Okay. More concepts, more. And again, as you could obviously imagine, sorry, there are no solution, explicit analytic solution to this equation, except the trivial ones. The trivial ones is when dn dt for both species is 0, you can find the fixed points. So, but because one of of the trivial, for instance, trivial solution is n1 equal to 0 and n2 equal to a certain equal to k2. Okay, so this obviously these are particular solutions, the fixed points, but we don't know the solutions of the system. Therefore, we'll have to go for some more qualitative analysis of these equations. Okay. Qualitative analysis, so we will look for fixed points, but before going for the fixed points and trying to know if the fixed point is stable or unstable and so on, let's do some manipulation with the equations, okay? So these are actually trivial manipulations. If you are not trained in math, please pay attention. It's nothing that is conceptually difficult, but pay attention. So first of all, I want to rewrite these equations in a form that is more suitable for analysis. So what I do is, instead of having this term here, for instance, I have R1, N1 times 1 minus N1 over K1 minus A times N2. I would like to have both factors with a K1 at the fraction, okay? So I say just, okay, A, I will say I can just, A is as a number, I can write it in terms of a new number, which I will call AB1 divided by K1, okay? We agree I can do this. A is a number, okay? Say 10. Now I can say, okay, and this is another number, okay? 5. So I can write this one in terms of this new parameter, okay? It's exactly the same. I'm just dividing. I'm not manipulating and I'm not doing anything new, okay? I'm just defining that I had a parameter which I called A, and now I substitute this parameter for the new parameter, which is the old A divided by K1, multiplied by K1. So I can do this, and I get this, which is the usual way that this system is written. So you have two parameters, B12 and B21. B21 obviously is related to this guy here, okay? And they are, again, the strengths of the competition between the populations, okay? Okay. After the analysis, I will make a critique of using this kind of model, which has to do with the fact that B12 and B21 are not mechanistic parameters, because we are building a model which we call phenomenological, because we are not describing mechanisms. Mechanisms would be to put the resources into the game. We are not doing this. Okay? So for this time, for the moment, this is what people in physics would call action at distance. Okay, population 1, population 2 here, and somehow they influence negatively one another. Okay, so you could ask, okay, I mean, what this seems magic. Okay, this black magic, like okay. Now, obviously, we know that what's behind is that there's a mediator, which is the resource. Okay, but in the model we don't have the resource. Okay, so at the point of view of the model, this is what we call a phenomenological model. We are not modeling all the mechanisms. So, okay, equations, and now let us pay attention to how many parameters these equations have. So we have 6 parameters, okay? And you will probably remember from yesterday's evening talk that many parameters is not good, okay? So if you want to know about the general solutions or the general qualitative behavior of the solutions of these equations, you have a parameter space which has dimension 6, right? And this is the simplest model with 2 species with competition. Imagine that they have 3 species and more biological phenomena, parameters multiplying, and no. So there are what we could say the good parameters and the bad parameters. The good parameters is the ones that you know. Okay, so it's if you have a model, you know the parameter, it's okay. Okay, but in many cases you have a parameter, but you don't know the value. Therefore, you should analyze these equations or your model and consider the possibility of different solutions depending on the value of the unknown parameter. So parameters can be a disaster sometimes. Okay, so this is also important beyond to the lecture here on competition. When you work on models, okay, you are interested in not having too many parameters, okay? Because with too many parameters, and this is something that everybody who has studied a little bit of statistics also knows. Okay? With too many parameters, I can actually have equations that describe everything, anything. Okay, I have a fixed point, or I have chaotic solutions, or whatever. And if I have a lot of parameters, I go to the lab or to the field, and I see, oh, I have a fixed point. And you find parameters in your problem that give you a fixed point. Then you go to a lot of situations, you have oscillations, and okay, modify the parameter because it's an unknown parameter. So fitting parameters, when you have models and you want to fit data with parameters, okay, having too many parameters will be a disaster. Okay, that's the same thing as trying to fit. Say you want you have a measurements, okay, that in a more elementary thing. Okay, you have measurements of a certain function, and well, say you have a function x of some variable here, t, and you get some points here. Say you have 1. These are your experimental results. Okay. So you have this, okay? If you have only 2 parameters, you can only fit a line, okay? Which would say this, okay? If you have now 6 parameters, which means polynomial of 5th order, I can actually make this, okay? Fits perfectly, okay? But is it better or not? It's not necessarily better, because you have, in this case, you have noise, okay? So it's not necessarily better. So when you work with data, okay, you should be aware that the proliferation of parameters can be a problem. This is called overfitting, and the same concept can be used for when you have data and your models. If the model has too many parameters, it fits anything and predicts nothing, okay? Because with this case, that's a famous case, okay? Say this is something like this, and this would maybe go this and this like this. And sometimes this is just better because it's not fitting the noise. So in the case of differential equations, it's not very different, okay? Well, this is a case of regression, but here we have differential equations. You also have parameters. If you have data, you want to find a fit of the parameters. If you have too many, you have actually a problem, not a solution. But there's a famous guy called. You had an observation? Huh? There's a famous observation by a famous mathematician and physicist von Neumann, who says, give me 5 parameters and I can fit you an elephant. Give me 6 and I can make his, how do you say this in English? Wave the, not only the tail, well, okay, then you need 7 for the tail. Okay? With enough parameters you fit anything, so, okay? I don't know, this is in English, trompa. I don't know. Okay, so let's go back. So 6 parameters, but now be prepared for some magic. We will find a way to have less parameters. Okay, isn't that a good idea? Well, I hope I've convinced you that it's a good idea to have less parameters. And we will get less parameters. What will we do in order to get a smaller number of parameters? So, we will define new variables. Okay? The variable, I will say n1 over k1, which appears in the equations, I will call it u1. Okay? I just had the variable n1. I divide, which is the population of species 1, and I divide it by the carrying capacity. So it's the proportion of the carrying capacity, okay? So it's equivalent. And the same thing for n2. And a little bit more tricky, I will say I have a time variable, tau, which is t times r1. Remember that r, the intrinsic growth rate, has dimensions of 1 over time. Therefore, this tau has no dimension, because this is 1 over time and this is time. This is a dimensionless variable. Okay? And these are also dimensionless variables. So now I have variables that do not have any dimension. It's dimensionless. Now I can use these definitions and see how the equations that I want to analyze look like in the new parameters, in the new variables. So instead of having an equation for n1, I want an equation for u1. Instead of having an equation for n2, I want an equation for u2. And the time should be rescaled here to the new variable tau. Okay? So that's not difficult to do. How would you proceed? I won't do all the calculations, but I would say I have dn1 dt. I will make it only for one of the equations, okay? 1 minus n1 over k1 minus b12 over k1 n2, okay? Then you say, okay, n1 is equal to k1 times u1, n2 is equal to k2 times i2. Yeah. What? I didn't say. On the board. Here? Where is the missing capacities? Ah, the N1 here, yeah, sure. Thank you. So, substitute, you will have d dt of n1 of k1 times u1 is equal to r1 times u1 times k1, 1 minus u1 minus b21 times u2 multiplied by k2 over k1. Okay? Now you can cancel this k1 with this k1, and you get d tau is equal to r1 of u1 1 minus this combination here times u2, which I will call a12. And the final step is to say, now I have to look at du1 dt. I wrote tau, but it was wrong, but t. Here, everything is t. And I want to transform to tau. So this is easy because t is just r1. It's just tau divided by r1. Therefore, gdt here, you substitute, you have d1 times g tau divided by r1, which is equal to r1 du1 d tau. And if you use this here, you can cancel the r1 here and here. Okay? Bigger, still bigger than that. So the final equation will be d1 d tau equal to u1 1 minus u1 minus a12 u2. Look at the first equation there. It has three parameters, r1, k1, and b12. And this only has one parameter. Nice, only one parameter. So, we disappeared with two parameters. Okay? So you can do the next step for the other equations. And actually, you can count the things like that. You have 6 parameters, but you have 3 variables, u1, u2, and tau, that you can rescale. And you rescale in such a way that they will subtract 3 parameters from my 6 parameters. And at the end, I will have 3 parameters. So the rescaled equations, if you do this algebra again and so on, will be just like this. And defining the a1 to a21 and the ratio of r2 to r1, you got this system of equations, which has 3 parameters. Right? So this is better for analysis than having 6 parameters. We have only 3 parameters. Right? What does it mean to have you'd say, okay, well, it's not intuitive, okay? You say, I have a system which has parameters that I more or less know what they mean. Now I have a system with only 3 parameters. This means that the behavior of the solutions of these equations depend only on a certain combination of my 6 parameters, which is this kind of thing here, like, you see, b12, k2 over k1. Okay? So It's only this combination that affects the solutions, the general behavior of the system. Okay? So I have 6 parameters in the original system, but only 3 combinations of these parameters are important for the behavior of the solutions of the system of differential equations. Right? So I can now proceed and analyze the behavior of these solutions in terms only of these 3 parameters, which are combinations of my previous 6 parameters. Now you would ask me, okay, but now we have, okay, we can do this, and we will do it. We'll look how the fixed points, stability, what happens to the system, how is the qualitative behavior of my solutions, and everything done in terms of these parameters. But you could also be more practical guy and say, no, but see, I have the equations and I have data. And I want to fit data to equations. Then I don't know how to fit these abstract parameters. Yeah, that's true. If you want to connect to data back, data is not non-dimensional. Has dimensions. Okay, time has dimensions, and the population is not given with respect to K1 and K2. Okay, if you want then go back and connect to data, you will have to know your 6 parameters. Okay? But the qualitative behavior of your system depends only on combination of these parameters, which are only 3 combinations. Okay? So here's the system of equations with my 3 parameters, and the way to proceed is to look for fixed point. Fixed points, as I hope you remember, are values of U1 and U2, which are constant, and are solution to the equation. And if they are constant, obviously, d U1 d tau is equal to 0, d U2 d tau is equal to 0. Okay? But if this is equal to 0, this means that U1 times 1 minus U1 minus A1 to U2 has also to be equal to 0, and this also has to be equal to 0. Okay? For, I will, here, sometimes to be more formal, you say this is not any U1, it's just the fixed point. So you say this is a particular, and you put a star here. It is a little bit of more. I don't have stars on my slides, but sometimes you put. Okay. So now I want to know the values of U1 and U2, such that the derivatives are 0. Therefore, the right-hand side of the equation has to be 0. And the right-hand side of the equation gives you this equal to 0 and this equal to 0. These are 2 polynomial equations for U1 and U2. Okay? And you can analyze this. Okay? So you don't have any more than a differential equation at this point for the fixed points. It's just an algebraic equation. And algebraic equations are objects that we know how to manipulate. Okay? So, these are the equations, the algebraic equations, and for U1 and U2, fixed points, and they have actually 4 solutions. Okay? So, how do you know that there are 4 solutions? It's not difficult. Look at the first one, this here. Okay? And there's an obvious solution, which is U1 equal to 0. Okay? Well, but when you go and plug U1 equal to 0 here, then there is an obvious solution, but there's a trivial solution that we don't even want to discuss, which is U1 equal to 0 and U2 equal to 0. Okay? Which is mutual extinction. Okay? But we won't consider this because, well, it's easy to show that it's not stable. Okay? So, if U1 is equal to 0, another possibility is that U2 is equal to 1, which gives you a 0 here. Therefore, one trivial solution is this one. Okay? Yeah.
I don't get what like this dimension as variable, but with these equations you can like draw a graph of the population varying over time.
Yeah, sure. But I mean, maybe your problem is tau. Hey, I mean, you can choose your time. I want to measure it in hours, days, and it's equivalent, okay? Hours, days, or just in terms of the R1. So I say my time is given in hours, but instead of hours, why not say I can have the time given in multiples and factors of R1, which is, okay? It's just a change of the scale where I want to measure the things. It's like changing from seconds to years. I mean, you can do this. It's just.
I'm really interested with that. Why you have that variable more than 2? Like,
Here?
Yes.
Well, because I didn't show you, but if you, I hope you believe me, if you do the calculation that I was doing here for the first equation, and if I do it for the second equation, I will have this variable rho, which is R2 over R1. Okay, variable, not a parameter. Okay, but again, we had 6 parameters. We have 3 rescalings. So we can eliminate 3 parameters. So at the end, we need 3 parameters. And the parameters is A12, A21, and rho. Okay. So, let me repeat again. Now, I have the differential equations, but I want to find the special solutions where U1 and U2 are constants. Constant population level. I impose that they are constant, and I look what values they have to have in order to satisfy the differential equation, which is now just as a 0 here. Okay? So you get this equal to 0 and this equal to 0, which means that you have a system of 2 polynomial equations, okay, 2 algebraic equations, which depend which are connected with, okay. And what I'm saying that there are trivial solutions, which is U1 equal to 0 and U2 equal to 1. Okay, let me write it. This is also one possible complete elimination. Then there's obviously some symmetry in the problem. I can have a solution that is U2 equal to 0 and U1 equal to 1. Therefore, you get a 0 here, this cancels with this, and this is equal to 0. Okay? So you have U2 equal to 0. Let me see. U1 equal to 1 and U2 equal to 0. And finally, I can have one more solution, which is just this thing equal to 0 and this thing also equal to 0. Okay? So you have to do is this is only this equal to 0 and this equal to 0 are 2 linear equations between U1 and U2. Okay? So you can substitute, say, U1 from here and into this equation and find U2 and U1. So I don't want to do this algebra. So I give you the solutions. The solutions are written here. This is the first one. This is the second one, third one, and this is the solutions that correspond to having this and this expressions equal to 0. So you have 4 different solutions. What they do represent the first is extinction of everything, end of the world. The one with U1 equal to 0 and U2 equal to 1 means that U1 got extinct, species 1 disappeared, and species 2 is at the carrying capacity, because remember, U1 was just N1 over K1, or N2 was, U2 was N2 over K2. Therefore, this solution means that U1 disappeared and U2 is on the carrying capacity. The other on the right-hand side means exactly the same, that U1 is at the carrying capacity and U2 disappeared, and the last one is a coexistence fixed point. Okay? So we had found 4 values of U1 and U2 that satisfy the differential equations and are constants. Okay? But now we want to know if these solutions, these fixed points, if they are stable or not. Okay? So how would you proceed? That's I won't do the calculation, okay, because it's a little bit longer, and you have to know like Taylor expansions and so on. But okay. But you would proceed saying, okay, now I say U1 and U2 are at the fixed point values, and I make a perturbation, and I want to know if this perturbation increases or decreases. If it increases, means that the fixed point is unstable, and if it decreases, the fixed point is stable. So I can do this mathematically. Okay, you need linearization, blah, blah, blah. So maybe it's too much to do on the blackboard. It would take half an hour maybe. So I will just give you the results. And then we go for some interpretation of the results. So analysis of the stability of fixed points will depend on the values of A12 and A21 of these 2 parameters. So the first fixed point, which is mutual extinction, is always oops. No, okay, this is different. So stability will depend on A12 and A21, and it will turn out, or from the calculations, that what is important is to know if they are smaller or larger than 1. So if both of them are smaller than 1, then the coexistence fixed point is stable. Okay? If both are larger than 1, then you have 2 different possibilities. U1 equal to 1 and U2 equal to 0, and the symmetric guy are both stable. You have two stable fixed points. Notice that in the first case, you had only 1 stable fixed point, which was the coexistence point. Now, with both of them larger than 1, you have 2 possibilities. And both possibilities are such that there's always the exclusion of one of them. One of them gets eliminated, and the other one stays in the system at the carrying capacity. And the final at the bottom, you have, if one of them is larger than one and the other one is smaller than one, then you always have one stable fixed point only, and it's the stable fixed point with the exclusion of one of the species and the not excluded species at the carrying capacity. So, depending on the values of these guys, you have different stable fixed points. Okay? So, we will do this. Let me show some plots about this. What does it mean? Okay. So, here are 4 cases of. I'm now plotting E2, a phase diagram, as we have done yesterday. Don't pay attention to these lines necessarily. These are called null lines and so on. It's useful to analysis, but we don't want to pay attention to this necessarily now. So, and let me go one by one. So this first one is the coexistence fixed point. Okay. Both populations are non-zero. They coexist. Okay? And this is only true, this is only stable if A1,2 and A21 are both smaller than 1. Okay? In terms of what does it mean? Does it mean that this is kind of a representative of the strength of the competition, means that competition is weak, then you can have coexistence. Okay. Now, if both of them larger than 1, then you have this situation here. The point in the middle, which is the coexistence point, is unstable. And you have 2 different stable fixed points, which is the one here, this one, and this one. So these are the fixed points which correspond to the elimination of one species and the prevail of the other species at the carrying capacity. So now you'd say, good, okay, I can have 2 possibilities, but in nature, if I start with population A1, A2, I will not randomly go to one fixed point and another fixed point. I will go for a definite one. To which point do I go when the time goes on? So let me draw this here. That's why there's this line. Here's one fixed point. Here's the other fixed point. Okay. And what happens is that if you give initial conditions, which are on this side, you go here. And if you have initial conditions of here, you go there. Okay? So there's a line that divides the points, which at the end of the day will go to this fixed point, and the other ones will go to this fixed point. This is elimination of population 1, and this is elimination of population 2. Okay? So this line is called a separatrix, because it separates things. And this region here okay, is called Bayesian of attraction of the fixed point, say this one, on Bayesian of attraction of this other point. Okay?
What is the function of this? Is something
No.
no.
Not possible to determine, even for the simple problem, analytically, the separatrix. It has to be done numerically. Only case where you can do analytically the separatrix is if A12 is equal to A21, and both them are larger than 1, then the separatrix is a line. And this is the trivial case, and it's not generic. Okay? So the separatrix, numerically it's not difficult to find the separatrix. So just because this is a line of unstable points. Okay? So if you go back in time, you will instead of going far from the separatrix, you will approach the separatrix. So numerically, it's easy to integrate back in time only. Just t to minus t, you get the separatrix. Louder?
How do you know the two fixed points are stable? Did you calculate the
Yeah. Jacobians and yeah, you have to do it. I mean, I didn't show how to do the analysis, okay? But this is usually what you have to do is write, say U1 now is the fixed point value plus some small increment. Yeah, Jacobian methods, all of this. But I'm avoiding this because, well, time and so on, but I'm just telling you the result, okay? If you want to go for the calculation, look at the book of Jim Murray, Mathematical Biology, and I guess also in the book of Mark Cott on elements of mathematical ecology. I think Britton also, which I don't remember, it's some mathematical biology, blah, blah, blah. Essential mathematical biology. And there you find this kind of calculations. It's straightforward. But well, I think it's already enough calculation for today. So this would be an extra class on stability of fixed points, Jacobians, and all of this. Okay. Where's my? So the interesting case here is that this means what? If both of them are larger than 1, I would call it strong competition. Okay, strong competition. Mutually strong competition. And this says that this one species will eliminate the other species, always. But which one will be eliminated and which one will prevail depends on the initial conditions being on what side of the separatrix you are. That's the message. So we have two more fixed points. One, this is the fixed point when A12 is small and A21 is large. In this case, you have A12 eliminates U1 eliminates U2. Species 1 stays, species 2 goes away. Is it easy to understand this? Yeah. Look, A12 being small means that the influence of 2 on species 1 is small, or it's weak, but A21 gives you the influence of species 1 on the dynamics of species 2, and therefore what this says is that it's a strong influence. So can be rephrased as U1 is a better competitor than the species 2. And in this case, you have elimination of species 2. And here you have the kind of symmetric case where the species 1 is eliminated and the species 2 stays at the carrying capacity, and this is symmetric when this parameter is large and this parameter is small. Okay? So, interpretation of the results is, means the following. So, A12 is a measure of the influence of species 2 on species 1, and vice versa. So, it's kind of a measure of the strength of the competition, and the analysis of the equations tells us that the important thing is if the parameters A12 and A21 are smaller or larger than 1. Okay, so if both are smaller, you have coexistence. If both are larger than 1, you have elimination depending on the initial condition. And if one of them is smaller and the other one is larger, the better competitor, the best competitor, is stays in the system, and the other one is eliminated. And here it's the symmetric case. So, okay, so this is the analysis. This is the qualitative analysis of this model. Okay? There's some comments to give here. One comment is, my equations have 3 parameters, A12 and A21. Oh, yeah. Mutual exclusion is not a stable fixed point here. If you don't, what does it mean? You don't have either one, there's nobody in the system. And you perturb this and you put some amount of population 1 and population 2, it will go to a fixed point which is not 0, 0. Will go to elimination of one of them or coexistence depending on the parameters. No, that's not the result here. The result is if competition is very strong, then one of them will prevail, but it just depends on the initial condition. Okay.
Then it's not like one exact initial point that will be.
So, good question. There is. If you sit on the fixed point, then you are always coexisting. Or if you sit on the 0, 0, then it's no populations. But the important thing here is that we should imagine that the systems are always under some kind of perturbation. Therefore, you try to be on one point. Maybe you'd have to have infinite precision to be on that point. Okay? If you don't have infinite precision or you have some perturbation, you will just go away from this point, and if it's unstable, it whoop, goes away. So having only the fixed points without knowing their stability is a trap. Okay, you say, oh, I have a coexistence, I have mutual exclusion, so on, but if they are not stable, they will never be observed. Okay? Because you need them to be stable, because you know your system. Either you don't have infinite precision for your variables, or it's been subject to small perturbations, but small perturbations will, if you are an unstable fixed point, it will go away from the fixed point. So you don't see the unstable fixed point. You only see the stable ones. Okay. So, but, okay. What I wanted to mention is, you have the differential equations, they have 3 parameters, A12 and A21 and rho. And rho was R2 over R1. No, R1, no, R2 over R1. This is rho. But the stability analysis does not depend on rho. Okay? Our results, rho disappeared from. So now I want you to have your imagination. So rho is the ratio between the intrinsic growth rate of species 2 divided by the intrinsic growth rate of species 1. And the stability analysis does not involve rho. Now I want you to give your imagination of, this is not completely true what I'm saying. Rho has some importance. Can you imagine how rho has some importance here? This is one thing, yeah, sure. So rho, because we only studied the fixed point, but we never studied how long it takes to get to the fixed point, okay? And this cannot be done by just looking at the fixed points. You need really the dynamics of the system, okay? It's not just, okay, I have the fixed point, bye-bye. No, you have the dynamics, and the dynamics is time evolution of the variables 1 and 2 will depend on rho. So how fast your approach to a fixed point will depend on rho. But there's still a second important instance where rho can be important. This is one. There's another one. No, not well. Not the trajectories, no. Because it's just how fast you go on the trajectories. Any guess? Separatics, yeah. This depends on rho. Okay, where is the separatics depends on rho. Okay, so this is the indirect effect of rho. Okay. So let's get back to more biological discussion. So what we saw is that if competition is weak, we can have coexistence, but if competition is strong, in any way strong, then we have always exclusion. Okay? So my world is a world of fixed points, and you can have only coexistence when you have weak competition, which means a lot of resources in general. Okay? And
when you have like a equivalence between R1
and R2,
one like you have like the four solutions, you have the extreme one, just one survive, or other survive. Then like the most extreme values for R.
No. The rho is only connected to how fast the population change in time, not to the fixed point itself. So it will go to the fixed point, and which fixed point it will end at the end of the day will depend on A1 and A2 and maybe on the initial conditions. Yeah? So it does not depend on rho. Which fixed point is stable or not does not depend on rho. Rho gives you because it's proportional to this derivative. When you look not anymore at the fixed point, so it's no zero here, it will be proportional to a time derivative. So means that the rate of change of the populations depends on rho. You can have extreme cases. Let's say this is a very small parameter or a very large parameter, means that the dynamics of one of them is much faster than the other one. Okay? So if this is a very small parameter, okay, this says that du2 d tau, which has a rho here, has a small parameter, that this changes slowly with respect to the changes of u1. And if this is a large parameter, vice versa. Okay?
Our college used the 6 parameter model, and I think that it did not have a separatist. Right?
Has no. The 6 parameters model is completely equivalent to this case.
Completely what?
Equivalent. The 6 parameters are still there. They are in A1 to A1. They are just like hiding, but they are there.
There is a solution for drawing the
No. Everybody wants to know, how do I get the separatics? It's not not made by analytical calculation. You cannot. For even, this is a very simple case of separatics and so on. No analytical solution for calculating the separatrix. Numerically, it's easy. But analytically, by doing calculations, I want the equation of the separatrix, you say. Okay, give me the equation of separatrix. Sorry, no way. So, in summary, our model predicts that that's more likely to have exclusion in nature than have coexistence, and this is known not directly from the model but from experiments. Has been named as the competitive exclusion principle. So it's named a principle, okay? Which is due to this Russian biologist Gause, who stated this in a book in 1932, very early result. And the experiments of Gause were performed with a protozoa group called Paramecia, and there are two species, Paramecia caudatum and Paramecium aurelia. Okay? So the experiment consists of, let me grow separately Paramecia caudatum and Paramecia aurelia, okay? Separately. And so I can see if they can grow, and then let me make a third experiment where I grow them together. Okay? I mix them. This experiment, here this is the original plots from 1932. Okay? Here you have at the upper part, left upper, is Paramecium aurelia, and on the right hand side is Paramecia caudatum. So they could grow. Okay, so that's experience where both of them can grow. But if you grow them together, you mix them, one of them dies out and the other one goes to the carrying capacity. Okay, so this is considered first experiment about exclusion through competition. Okay, they are competing for resources. Okay? Okay, but before I show you this example, which is now let us stop a moment and think. Let's think. You see, we have a problem here. Okay, I have a theory, Lotka-Volterra model for competition. It tells me that if competition is strong, you always have exclusion, and if it's weak, you can have coexistence. Then you say, but what does it mean to be strong? Oh, to be strong means that there's exclusion, and what does it mean to be weak? It means that you can have coexistence. Therefore, it's tautological. There's no way of knowing, because you would say a predictive theory, let's say I go for A12 and A21, I determine them independently of doing a competition experiment. And then I predict which species can eliminate the other one. But there's no way to independently calculate A12 and A21 without doing the experiment. Therefore, I cannot know these guys here. Okay? I cannot. And I could just do the experiment and fit them. Okay? But you see that this is a problem, because if you get elimination or you get if you get coexistence, you will always find A12 and A21 that fit it. Okay? So it's a completely non-predictive thing. You cannot predict. And that's a problem. And it's a problem due to the kind of formulation we have developed, which is a phenomenological thing, which is a phenomenological theory, where we just say that A1, the species 1 and species 2 have negative mutual influences. Right? But you're not saying how to know these parameters, and they are completely there are parameters that have to be fitted by the experiment. But the experiment would be supposed to validate the theory, but it will always validate anything. Okay?
With competition experiment, in this case, you mean keeping two populations
Together.
Follow the fate of populations, and that's all.
Yeah.
Because there are many other competition experiments.
Okay.
Experiments that you can do.
Yeah. Okay. So what I'm saying is, here, what I mean, I put them both together and I see, I follow the time and see which one, if they coexist or if they get eliminated or something. Okay, only that. And you go and say, okay, I will always find parameters that explain my results. So I always find parameters for any result. The theory is always, it's always true. Cannot be that there is no case that I can't explain. Okay? So it's really a problem. Okay? And that comes from the fact that I have postulated no mechanism. I have just postulated kind of influence, like magic influence of between species 1 and species 2. Then the question obviously comes, could I have done differently? And the answer is yes. Modern theory of competition beyond Lotka-Volterra goes on to model systems of competitor 1, competitor 2, and the resource. You need 3 equations. Okay? We won't do these calculations here, okay? Because it's not the case. But what you want is something like I have, usually we call it consumer 1, consumer 2, and you have a resource which is common to both of them, okay? And then you write an equation of the relation between interaction C1 with R. But this we know because this is yesterday's lecture. This is predator-prey or consumer-resource. This we already know. Okay? And then I do the same thing here. Okay? And then I have to give an equation how the resources is affected by the consumption. Okay? And how is the dynamics of the resource, like it's growing or is something which is externally manipulated or whatever. Many different cases. But you see, you can have one equation for C1, for C2, and for R. And you have 3 equations, and if that's all that you have C1 consuming only R and C2 consuming only R. You will have always exclusion. There's no coexistence. No coexistence. One resource, there's no way of having two consumers or 2 competitors on this. Right? It's not difficult, but I mean, okay, it's getting late. You can do this, write equations. And so actually this says that if I go for this, and now, you see, I'm not if I want to repeat the experiment, like Paulo said, I first grow them independently, C1 and C2, and then I go for the competition experiment. Now I can have parameters to predict the outcome because I grow independently C1 on R, I grow independently C2 on R, so I determine all the parameters, and that's it. Okay? And then I will have a prediction. Okay? Well, this situation where you strictly have only one resource, okay? Only one, okay? There's no alternative resource, then you have always elimination of one of them. Okay? Will be connected to the ability of consumption here, attack rate and so on. Yes, with one resource, yeah. So,
I really like this comment that you make about the philosophy, right? Although it seems to me that this isn't the answer properly, because this is an exploited competition, right?
yes.
As you stated first,
Okay.
it's a competition
For resources.
But it feels to me that there is still a hole in the theory when dealing with interference competition.
This is right. Okay, this is right. So interference. This is not an approach for interference. Okay, so you have to develop something else to treat interference. In which case, these guys now could be somehow mechanistics. Okay, because if you can make experiments about the interference properties before making the competition. Okay. So, okay, this is only for exploitative competition, which is widespread. And interference is, well, there's a lot, but it's not the general rule. But, well, then you would say maybe, because this is what in ecological jargon would be, you have complete overlap of niche. They have exactly the same resource. There's no alternative thing. But you could say, okay, now let us say I have two resources. Okay? Both of them can consume two resources. And in this case, you can have coexistence. Not always, but you can have. Okay? So two resources, you can have two competitors. Okay. With time varying resources, or the resources are variable here, okay? In the sense that they are functions of which are solutions of a differential equations for the dynamics of the resource. But you could also say, okay, my environment is not constant, okay? For instance, I could do some kind of manipulation to say the resources is something that in an experimental setting can be manipulated. So I put resources in. But I can do this and say in a periodic way or with different kind of possibilities. Then you can get, sure, then you can have situations where you have coexistence. Now, if I put a third one, consuming these two resources, well, you already guessed the answer. There's no situation where these three coexist. There will be only coexistence of two of them. Right? When they coexist, there is not necessarily specialized, because both of them can consume both, okay? But there will be a preferred resource. Okay? And well, at the end of the day, this means that if I have, say, n resources, I can have n species coexisting on the resources. Okay? That's the result of modern competition theory, where resources are explicitly modeled. This is the old-fashioned Lotka-Volterra theory, which gives you an insight. Okay? Because it was not obvious that you would always end on fixed points, and there are only two kinds, which is exclusion or coexistence, and there's only one coexistence point, and so there are a lot of insights that come from this, okay, that motivate the competitive exclusion principle. But well, it has a limitation when it goes to compare with data and so on. So a better way to approach this is to model the resources, which poses obviously a new problem, because you have to know the dynamics of the resource. Okay? So you have to do this, you have to know. And sometimes this can complicate your life, because maybe the resource feeds on a more basal resource, and so on. You got a network. Okay? But then you see immediately that, well, I have a network, but then I could have also somebody consuming this guys, and a network of traffic interactions. Okay? So somehow you have to manage to, because this would take you to, if you really stick to the idea that you have to model everything, you will actually come to the result that you have to model everything, really, all species. It will be impossible. Okay? Somehow you have to cut down and simplify your system. Okay? Usually in the simplest case, you simplify the dynamics of the resource. Right? You say that somehow you know it. Very good. So this, yeah. You put a logistic equation, and then you have to put the consumption of how the consumption affects the resource. But this is the easiest thing is put a logistic equation for the resource in absence of the consumers, and then you put some two new terms, one for the consumption for consumer 1 and the other for consumer 2, and that's it. That's the easiest way. Yeah.
We came up with, in my point of view, known trivial result that we should be modeled as a one species interaction.
Ah, the single species case, yeah.
So this kind of reasoning, is there any heuristic laws or heuristic guidelines for us to model like a complex?
Yeah, well. The point is, say now you have a network and so on, and well, then you can. It depends on many things. Is it a traffic network? Is it competition network? Mutualistic networks? If you have more competition, then you have only fixed points. But if you have predator-prey network, you know you can have oscillations, and then you can have. You can have dynamical coexistence. Okay, no fixed points, but coexistence in a dynamical way. So it's a whole branch of things that you can have. Okay, so we will have to give up the total generality, because here we are being really general. I mean, I just say two competitors, okay? I'm not saying that animals, plants, or whatever, bacteria. Yeah, but well, if you want to go for networks and so on, you have to start to say, okay, now I want situation which is more specific, and then you can do things. So finally, let us. Okay, this was just one example situations where you have competitive exclusion in the field, okay, which are the competing between what people call the Argentinian ant and the Californian one, which have their names here. And in the Argentinian ant has been introduced in California, and turned out that progressively the Californian ant has been eliminated and the Argentinian ant has been introduced and dominates the situation. Right? So this is a result of competitive exclusion in the field. So finally, we have a problem because, you know, glories and miseries of our models. So I showed you the glories of the Lotka-Volterra one, but then I destroyed it saying that I need the resources. And I am telling you that the result of including resources will tell you that if you have n resources, then you can have n species coexistent on the n resources. So, nice. Then we come to the problem of the paradox of the plankton. Paradox of the plankton is the following. The phytoplankton. Okay, phytoplankton, you can usually not see it just looking at this, but from the space, sometimes you have blooms of phytoplankton like this here. And actually, it's what's needed for phytoplankton is just light and inorganic molecules. Okay? And the paradox is the following. There are many species of phytoplankton. But the number of resources, which would be just how many? 5 or 6 elements, like nitrogen, potassium, I think, or something, only a few elements, okay, and light. Therefore, you would expect not more than 5 or 6 phytoplanktons coexisting, but that's not true. Actually, there's coexistence of thousands of species of phytoplankton. Right? So, maybe everything is wrong. So, problem, yeah, problem. The observation that, and you can do experiments. You can really, you can control your resources in a laboratory setting, and you can enforce that the resources are such that the competitions are strong, because you can have only a few resources, not too much. Then you would expect always that you have a maximum number of up to 10 species, but you see thousands. Okay, so this is a paradox which is illustrative, and so you could ask, well, how could I explain this situation? So maybe you can give me some guess. How could I explain the coexistence of so many species of phytoplankton, which obviously is not a problem only for people that work with plankton, because you look at the nature and there are so many species. So then comes the question, why are there so many species? Okay, which is a famous title of a work by George Evelyn Hutchinson. It's a famous book which introduces some theoretical ideas in ecology, but just staying to the phytoplankton, what do you guess could be a biological explication? Forget the models now, okay? The models only tell me that you should have elimination. So if you don't have elimination, what is the mechanism that you expect to be important in order to have so many species coexisting?
One thing is exactly this biodiversity. Like you have a lot of predictions on that.
Okay, one possible thing is this system is not composed only by resources and phytoplankton. There's probably a zooplankton, yeah. And but I mean, I don't know if you can control this in lab. I don't know, but this is a way. Okay, say you are talking on a kind of closed system here, but there could be other guys in the system, and maybe there could be a situation where coexistence is impossible. Yeah, that's one possible solution. There are other ones. Hmm? Hmm? Oh no, adaptation is a different time scale. Okay, it's a much longer time scale. Hmm? Even for plankton. Hmm?
Consider the equations and deterministic equations. I always like the idea that doing the same profit level,
Mm-hmm.
we have the profit.
Yeah.
So the parameters,
Hmm.
each parameter,
Mm-hmm.
each dynamics.
Yeah.
Just forget about it. So the species are coexisting in
You mean a kind of neutral way? Yeah. Well, still this does not give you an answer. I mean, you have situations where you have experiments with other species, but where you see elimination, and actually the idea of exclusion by competition is a driving idea that is even behind the idea in theory of evolution and so on. That you can have the best competitor will outcompete the weaker competitor, and so it is an idea that it's not just that it's a mathematical result from the equations, but it's something that should happen. So what would be the possibility of having? Why are there systems where you have exclusion, and why do you not have exclusion in other systems where you would expect to have exclusion? Okay, okay, this is a complicated thing. You could say, yeah, the system is really not in equilibrium. And maybe one thing is you say, okay, you are in a system that's constantly perturbed and so on. Well, this is a debate. Okay, Paulo, you have been involved in it. This is like the intermediate perturbation hypothesis, kind of, yeah. So it's possible, but I mean, that's undecided. Perturbation alone can give you this. Ah, this is nice. So we are not talking about the spatial dynamics here, okay? Spatial dynamics is not taken into account. There's no space. We are doing population ecology only with the populations, not their spatial distribution. Well, and you can have inhomogeneous habitats, right? Which says maybe there's one species which is does perform well in a certain part of the habitats, but not in another part. Okay, that's the idea of refugia. Okay, you have a place where you have advantage over the other ones in different places because there are homogeneities on the habitat. Maybe they have coexistence because the habitat is just not homogeneous. This is a possibility. Sure. Okay. Yeah, okay, that's what the first idea was. You could have more things here, okay? So maybe you would have to take into account always the complete networks, and maybe this conclusion is still too simple as a model to try to try to say from this model, then saying that you would expect this in nature, and say, okay, but nature has always more connections here. Okay? This is a possibility. Yeah. Huh? Temporal variations. Yeah, you could have temporal variations. Depending, a temporal variation is also tricky, right? Because depends. Yeah, I'm not sure that this can be used for explaining. Yeah, if the temporal variation is such that at a certain, very precise temporal variation, such that the temporal variation affects the competitive ability, you could have, well, you have a seasonality thing, and then there's a species 1 that, say, outcompetes species 2, but in the winter it's the opposite, and the time scale is such that they never reach the zero, and then you can have kind of temporal variability, but with certain regularity, like seasons. Okay? Just random temporal variability, I don't think will work. So more ideas.
Maybe related to the spatial variation we were talking about. Your resources is really such a vague thing to say.
Mm-hmm.
You know? I mean, you said it like nitrogen. I mean, for example, it could be, let me start again. It's very fictional, the classification we do on resources. You know, maybe it's not like simply nitrogen. Maybe the resources are operating at a scale which is not finite, and accordingly there are more resources, but let's say sun energy or nitrogen.
For the point is about phytoplankton. Phytoplankton is a basal thing, so it has only these resources. This argument would be true if you were talking about higher order organisms, more complex things. The paradox of the plankton, the strength of the thing, comes from the fact that this is really only feeds on inorganic matter.
Right.
And
it could be inorganic matter here. So R is resources, right?
Mm-hmm.
You have inorganic matter. But I could say, no, there is not just one resource. There are two resources.
Yeah, there are like 6 or 7.
Right. Suppose there is just one.
Okay.
I'm going to make 2 out of 1. How? I'm going to say it's not only inorganic matter, but inorganic matter here and inorganic matter there.
Okay, but this means that we have spatial variation somehow.
Right.
That should be something different from one place to the other.
But you see how it's not well defined how many resources you have. It feels in.
No, I mean, now the number of resources is defined, but I mean the distribution of the resources in space can be such that you can have something like coexistence due to the non-homogeneous character of your habitat. This is possible, but I mean the number of resources that the phytoplankton consumes is very limited. That's the strength of the example of phytoplankton. If you tell me, no, I'm talking about, I don't know, fox and rabbits and so on, I agree with you. But the phytoplankton is something that you know that resources are limited, okay? And you can define them because they are elements, chemical elements, okay? In this case. Yeah. Okay, and this could be, but this is again a spatial thing, okay? So you can have spatial variations, non-homogeneous habitat, and the performance depends on where you are in your habitat, okay? Possible, but it boils down to the same explanation of spatial variation, okay? Well, if we are talking about plankton, I don't think. Okay. For plankton, I don't think there will be mutualism. I mean, intuitively, I'm not a specialist on plankton, but I don't think there will be any mechanisms to promote mutualisms. For other species, yes, but this is again an explanation saying that, okay, there are other things happening here, okay? We are just not taking into account all possibilities. And one simple case, it's not mutualism, it's just I have consumer 1 and consumer 2. Consuming resource 1, the only resource. You expect elimination of one of the species. But now say one of the species is able to predate on the other one. Say C2 can predate on C1. Then maybe you can have a situation where C1 would eliminate C2 because it's the best competitor, but it doesn't because C2 is able to prey on it. This, okay? If this is called an intra-guild situation, okay? Intra-guild is this: you have a resource and you would expect elimination, but as the best competitor maybe is predated by the other one, this can give you a kind of balance, and it's possible to happen. So in this case, in a simple case, you see, you have not only consumption of so you can have this kind of relations with intra-guild relations. It exists. This one is not rock, paper, scissors. This one is observed in many situations. It's obviously it's not the first thing you see in your life, but people do many experiments with this.
Cases where they put 3 bacteria, it never happened. Like rock, paper, scissors.
But it's not rock, paper, scissors. Rock, paper, scissors would be here.
Oh, okay, so you have
Consume, and predation. It's not rock, paper, scissors. Okay, it's not a game. It's, no. It's not like this. Okay, 2 consumers and a predation relation. It's not rock, paper, scissors. I agree. Rock, paper, scissors is. I don't know if this is actually, or if it exists. It's really exceptional cases. But this exists widely. Okay, you can do experiments and so on. Yeah. At a certain? Mm-hmm. Yeah. So you can formulate everything what you have done in the summer course in terms of probabilistic dynamics. It's called stochastic processes, and you can formulate this. Okay, it will give you results that are a little bit strange. Like if you have a 2-species dynamics, it always gets mutual extinction after a long enough time. Because the probability of mutual extinction is never 0. Maybe it's very small. So you will talk about probability of extinctions and so on. Okay, so I don't know if this can be considered an answer to the problem, because what you will get if you have a very strong competitor, you have a very small probability then of having coexistence. Okay, so if you have a small probability of having coexistence, well, okay, can you observe sometimes? Maybe yes. So still, it's true that you will have coexistence, but it will also be not very probable. Okay? Yeah, okay, that you can do, and the results don't change. I can do this with